All right, I am now going to walk through Review Lab 3. This is the Airplane on a String lab. And in this investigation, we have this video of an airplane on a tether going around in a circle. And you can see that it is attached to a spring gauge, which shows the tension in the string. The very first question here is simply to apply Newton's second law in the vertical direction to determine the mass of the model plane. So if I begin with a free body diagram of the plane, I circle my system being the plane. There are only two forces acting on it, the gravitational force downward and the tension force in the direction of the string. If I do my Newton's second law evaluation of the forces in the vertical direction, that's specifically what the question asks. It says apply Newton's second law in the vertical direction, determine the mass. Looking at the vertical direction, I see that the force of tension, this vertical component of the tension force, is equal to the gravitational force downward. So this upward component of the tension has got to be equal to the gravitational force downward, and that vertical component is this tension. This is the hypotenuse of this right triangle times the cosine of this angle is equal to the mass of that airplane times the gravitational field strength. And I can rearrange that to find that the mass is equal to the tension times the cosine of the angle divided by gravitational field strength. Now, point of caution here when you are making these measurements is that when the video starts off, the airplane is behind the plane of view. And so if you make this angle measurement, I'll go ahead and bring up the protractor here. If you make this angle of measurement at the start of the video, you are not measuring the correct angle. The correct angle that you need to be measuring is here when it is either at its furthest to the right or here when it's furthest to the left. And in either case, that's about 52.5 degrees. Okay, so you want to make sure that you are making your correct measurement about 52.5 degrees. So if I use 52.5 degrees and the tension that I see in this spring force meter is 6.5 newtons, that gives me a mass of the airplane of about 399 grams, about 0.4 kilograms. The second question is to use Newton's law in the horizontal direction to predict the radius of that circular path. So if I use that same image, if I'm now looking horizontally, the net force horizontally is the horizontal component of this tension. So this now is the tension times the sine of this angle. Again, that's the net force horizontally is this horizontal component of the tension. So Ft sine theta is equal to the net force on any object is the mass times the acceleration. In this particular case, obviously, since this airplane is traveling in a circular path horizontally here, this is a horizontal path that it is circumscribing. That is centripetal acceleration. So it is the net force is equal to mass times the centripetal acceleration. This is harkening back to Unit 2 when we looked at circular motion And centripetal acceleration is defined by the tangential velocity squared over r. And here in the problem, it gives you the hint that this tangential velocity, reminder, is 2 pi r, that is the circumference, the distance that the plane travels, divided by the period, capital T, that it takes to traverse that distance. So looking again just at the net force statement here, the net force horizontally is the tension times the sine of the angle, which is equal to the net force, mass times acceleration, mass times centripetal acceleration. If I now just replace v squared by 2 pi r divided by t, what I have ultimately is ft sine theta is equal to m times 4 pi squared r squared over t squared r. And if I solve this for r, making the substitution from above that mass was the tension times the cosine of theta divided by g, what I end up with is a radius of t squared times the tangent of theta times g divided by 4 pi squared. And if you plug all of that in, you would estimate a radius of about 0.39 meters. Notice that once you make your predictions, it's going to lock your answer. And this will then give you the opportunity to use the ruler tool to actually measure that radius of that circular path. And when I put the protractor and the ruler back on and advance the video to where the plane is again at 52.5 degrees, I see that the actual radius to the center of mass, I'm going to estimate the center of mass to be about right here. So I get 0.44 meters. My estimate had been about 0.39 meters. So I get is that a value that I predicted was 10.7% off from the value that I measured, and I would make some plausible explanation as to why that might be.